Hello students, I am Professor Dheeraj Kumar Singh from Department of Mechanical Engineering, Sagar Group of Institutions, Sistekar Bhopal. Dear students, today we are going to discuss basics of first law of thermodynamics. So first of all, let us see that what are the topics we are going to cover today. So we will cover today first topic, slope of isothermal curves and adiabatic curves on PV diagram. Our second topic is ideal gas equations for various processes. Third is first law of thermodynamics discussion. Fourth is consequences of first law of thermodynamics. And remaining these two, heat transfer in various non-flow and closed system processes and numericals, we will be covering next video. So today we are going to cover these four topics. So let us start. So our first topic is slope of isothermal and adiabatic curve on PV diagram. So first of all, dear students, we have to understand how we represent isothermal and adiabatic curve on PV diagram. So we can see the first curve is isothermal curve and the second one is adiabatic curve. We can see the adiabatic curve is little bit steeper than isothermal curve. So why adiabatic curve is little bit steeper than isothermal curve and why the slope of adiabatic curve is more than isothermal curve, we are going to see here. So we all know dp by dv is the slope, right? If we will take v in x direction and p in y direction, then dy by dx would be our slope. But here we have taken p and v axis, so dp by dv will be our slope. And this is an isothermal process, so temperature is constant in isothermal process. So now we will apply ideal gas equation here. So we all know ideal gas equation, PV equal to mRT. So as we know in isothermal process, our temperature is constant, so PV equal to constant. We can write the whole term mRT and we can treat the whole term mRT as constant, as our temperature is constant. So on differentiating this PV equal to C, we will get PdV plus VdP equal to 0 because the differentiation of constant is 0. Then we will take VdP into the right hand side, then we will get PdV equal to minus VdP. And when we will arrange it, then we will get dP by dV equal to minus P by V. So this is our isothermal slope, dP by dV equal to minus P by V. Now we will move on to adiabatic process. So the equation of adiabatic process is PV to power gamma equal to constant, where we all know gamma is our adiabatic index and it is 1.4 for air. So now we will differentiate it for getting the term dP by dV, our slope. So when we will differentiate it, then we will take P as a first function and V to power gamma as a second function, right? So P dot gamma dot V to power gamma minus 1 dV plus then here V to power gamma as first function and P as second function plus V to power gamma dot dP equal to 0, right? Then we will arrange it. P into gamma dot V to power gamma minus 1 dV, and we have taken V to power gamma dot dP into the right hand side, so the sign will change. It will become minus V to power gamma dP, right? Then we will arrange it again. P into gamma dot, then we have written V to power gamma minus 1 as V to power gamma divided by V, dV equal to minus V to power gamma dP. So V to power gamma and V to power gamma in the left hand side and the right hand side will get cancelled out. Then what will be remaining? Then dP by dV equal to minus gamma divided by minus gamma into P divided by V. So we are getting here our slope dP by dV equal to minus gamma P by V. So we can compare this adiabatic slope with the isothermal slope. So adiabatic slope is gamma times higher than the isothermal slope. So we have written here dP by dV equal to gamma into minus P by V. So very clearly we can see here our adiabatic slope is gamma times larger than isothermal slope as gamma is greater than 1. So now we can conclude it very easily that yes, adiabatic slope has more value than isothermal slope, and adiabatic curve is more steeper than isothermal slope. Why? This is because adiabatic slope is gamma times higher than the isothermal slope. Then move to the next slide. Now we will discuss the ideal gas equations for various processes. So first process is constant volume process. So constant volume process, in constant volume process V equal to C, and when we apply ideal gas equation PV equal to MRT, then we can treat volume as a constant. Then when volume will be constant and MR, we all know that it is also constant. The M is the mass of the gas and R is the characteristic gas equation. So these are also constant and volume is also constant. That means our P pressure is directly proportional to temperature T. Right? So here in this diagram we can see PV, on PV diagram, heat is supplied from 1 to 2 and heat is rejected from 1 to 2. So how can we write the equations? So here we can see our pressure is directly proportional to temperature, so we can write it very easily, P2 by P1 equal to T2 by T1. So this is our ideal gas equation for constant volume process. Now move next to the constant pressure process. We can see heat is supplied from 1 to 2 and heat is rejected from 1 to 2 here in this process. When heat is supplying, volume is increasing. When heat is rejected, then volume is decreasing. So when pressure is constant, then we all know volume will become directly proportional to temperature. So here volume is directly proportional to temperature and we can write V2 by V1 equal to T2 by T1. Now move to isothermal process. In this graph we can see 1 to 2 is isothermal expansion and here 1 to 2 is isothermal compression. When expansion process will take place, then pressure and volume both will decrease, and when compression process takes place, then pressure will increase and volume will decrease. Right? Once again I want to say, I think I have said something wrong here. In PV, when isothermal expansion process will take place, then volume will increase and pressure will decrease. And in isothermal compression process, volume will decrease and pressure will increase. So we all know temperature is constant. So here in the right hand side in MRT, all three terms will become constant. So PV equal to constant. So we can write the equation for ideal gas is P1 V1 equal to P2 V2 for isothermal process. Now adiabatic process. We all know the equation of adiabatic process, that is PV to power gamma equal to constant, and here we can see in 1 to 2 adiabatic expansion and 1 to 2 here is adiabatic compression. So I have already discussed in isothermal process, when expansion will take place, at the time volume will increase and pressure will decrease, and when compression will take place, volume will decrease and pressure will increase. So from ideal gas equation we have applied PV equal to MRT here. So we can write P equal to MRT by V, taking V in the denominator of the right hand side. So our equation 1 is PV to power gamma equal to constant and equation 2 is P equal to MRT by V. From these two equations we can put the value of P in equation first. So after putting the value of P in equation first, we will get MRT by V dot V to power gamma equal to constant, and we will take this denominators V to the numerator, then we can write MRT V to power gamma minus 1 equal to constant. And we all know MR is also we can also treat MR as constant, so we are taking MR in the right hand side, the denominator. So TV to power gamma minus 1 equal to C by MR, and C by MR is also a constant. So TV to power gamma minus 1 is constant. So we can write our ideal gas equation here very easily, like T1 V1 to power gamma minus 1 equal to T2 V2 to power gamma minus 1. Or also we can write this adiabatic equation like P1 V1 to power gamma equal to P2 V2 to power gamma. Or if we want to write it in terms of temperature and pressure, then we can see here T2 by T1 equal to P2 by P1 to power gamma minus 1 by gamma. Similarly, dear students, we can write the ideal gas equations for polytropic process, because in adiabatic and polytropic process there is a very minute change in index only. Here we are using Pb to power gamma equal to constant, gamma is adiabatic index, and here Pb to power n is equal to constant, n is here polytropic index, right? So basic difference between adiabatic process and polytropic process is that in adiabatic process only work transfer takes place, heat transfer is zero, but in polytropic process both heat transfer and work transfer takes place. So similarly the equations will be similar in polytropic process as of adiabatic process. So P1 V1 to power n equal to P2 V2 to power n, then T1 V1 to power n minus 1 equal to T2 V2 to power n minus 1, and last T2 by T1 equal to P2 by P1 to power n minus 1 divided by n. And all these equations are valid for polytropic processes of an ideal gas. Now dear students, move to the first law of thermodynamics. This is also known as Joule's law, or this is also, we also know it by the conservation law, energy conservation law. So let us discuss the first law of thermodynamics. So before discussing these figures, figure of adiabatic work and this second figure, I want to discuss some of the basic things of first law for a closed system undergoing a cycle. Dear students, we all know the transfer of heat and the performance of work may both cause the same effect in a system. For an example, heat and work are different forms of same entity called energy, which is conserved. What I have said, that heat and work are different forms of the same entity and both will be known as energy, which can be conserved, means energy can be conserved. So energy which enters a system as heat may leave the system as work, or energy which enters the system as work may leave as heat. Both things can happen, right? So let us consider here in this figure, let us consider here a closed system which consists of a known mass of water contained in an adiabatic vessel. Adiabatic vessel means heat transfer from this vessel is zero, means this boundary is insulated, there will be no heat transfer, right? So let us consider a closed system which consists of a known mass of water contained in an adiabatic vessel having a thermometer, this is a thermometer, right, and a paddle wheel, this is paddle wheel, as shown in this figure, adiabatic work figure, right? So let a certain amount of work W1 to be done upon the system by this paddle wheel. This paddle wheel has done some work on this water, right? So in this figure we can say 1 to 2, W1 to, right? So let a certain amount of work W1 to be done upon the system by a paddle wheel. Then the quantity of work can be measured by the fall of this fall of weight which drives the paddle wheel through a pulley, right? I am repeating once again, the quantity of work can be measured by the fall of weight which drives the paddle wheel through a pulley. So the system was initially at temperature T1, the same as that of atmosphere, and after work transfer let the temperature rise to T2. Then the pressure is always 1 atm, okay, outside inside. Then the process 1 to undergone by the system is shown in this second figure, 1 to 2, W12, right? So the system and the surrounding, now what we will do, let us remove this insulation. what we are doing, if I will remove this insulation, right, this adiabatic vessel, if I'll remove this insulation, then system and surrounding interact, right, the system and surrounding will interact with each other, and the system and surrounding interact by heat transfer till the system return to the original temperature T1. Now the temperature has become T2 when we have removed this insulation, then again the temperature of this body will go back to T1, attaining the condition of thermal equilibrium with the atmosphere. So the amount of heat transfer Q21 here, the amount of heat transfer Q21 we can see in this process, right, the amount of heat transfer, right, in Q21 from the system during this process, right, can be seen here very easily, 2 to 1, right, and it can be estimated, so the system thus executes a cycle which consists of a definite amount of work input W12 to the system, followed by the transfer of an amount of heat Q21 from the system. So it has been found that this W12 is always proportional to heat Q21, right? So it has been found that this W12 is always proportional to this Q21, and the constant of proportionality is called Joule's equivalent or the mechanical equivalent of heat. When we will equate these work and heat, then we will get a constant of we will get a constant of proportionality, that is known as Joule's equivalent or the mechanical equivalent of heat. So in the simple example given here, we can understand each and everything, right? So here let us consider a closed system which consists of a known mass of water contained in an adiabatic vessel having a thermometer and a paddle wheel, right? And we have discussed all the things, that how temperature will increase from T1 to T2, okay? And when we will remove this insulation, then again that temperature one regains its original temperature T1, and then how cycle will complete, then 1 to 2 is work and 2 to 1 is heat, right? So cycle completed by a system with two energy interactions, adiabatic work transfer W12 followed by heat transfer Q21. Now we will understand the statement of first law of thermodynamics, right? In the earlier slide we have seen that how work can be equated to heat transfer, right, and how both can come to equilibrium with each other. Now we will understand the statement of first law of thermodynamics. For a closed system undergoing a cycle, net heat transfer summation Q is equal to net work transfer summation W. This is the statement of first law of thermodynamics. So we can write it like that: summation W cycle equal to J summation Q cycle. J is nothing but the constant of proportionality or Joule's equivalent, or we can say it mechanical equivalent of heat, right? Where J is the Joule's equivalent, and this is also expressed in form cyclic integral del W equal to J cyclic integral of del Q, right? So where the system cyclic integral denotes the cyclic integral for the closed path, this is the first law for a closed system undergoing a cycle. So now we are having the expression for closed system, first law of thermodynamics, right? So this is the first law for a closed system undergoing a cycle. So the equation is summation W cycle equal to J summation Q cycle. Now moving further, in the SI system of units, both heat and work are measured in the derived unit of energy, the Joule. The constant of proportionality J is therefore unity, right? So summation Q is equal to summation W. We can remove J from here, right? And we can write J is equal to 1 Newton meter per Joule. As we know, J can be written summation W by summation Q. So we all know that unit of heat is Joule and unit of work is Newton meter. So we can write Joule as 1 Newton meter per Joule. So now our first law of thermodynamics valid for a cycle equation is summation Q equal to summation W. We have already discussed that we have to discuss consequences of first law of thermodynamics as our fourth topic. So what are the consequences of first law of thermodynamics? Consequences means outcome. What are the outcomes of first law of thermodynamics? So first consequence we can see here, heat transfer is a path function. We have already discussed, students, that work transfer is a path function, right? But here in first law of thermodynamics, first consequence is heat transfer is also a path function. How heat transfer is a path function, we will understand it by this diagram and by this equation. So we can see here the process A is going from point 1 to 2, and process B and C is going from point 2 to 1, right? So there are two cycles. First cycle is 1A 2B1, 1A 2B1, and second cycle is 1A 2C1, right? So now we will apply first law of thermodynamics for closed system in a cyclic process equation here. So we can write summation Q equal to summation W. And we have applied this equation for first cycle and for second cycle. Means cycle 1A 2B1 and 1A 2C1. So we can write equations like this: del Q 1A2 plus del Q 2B1, which is equal to del W 1A2 plus del W 2B1. How we can write these equations? Because first of all we have to take the summation of heat in a cycle, then we have to take the summation of work transfer in a cycle. So when we are taking the summation of heat transfer in a cycle, so we can write it del Q1A2 plus del Q2B1, and when we will write the equation for work, then we can write del W1A2 plus del W2B1, right? So this we have written for first cycle. Similarly for second cycle we can write del Q1A2 plus del Q2C1 plus del Q plus del W1A2 plus del W2C1, right? So for both cycles we have written the equations. Now we are going to equate these equations. Then what we are getting? When we are equating these two cycles equations, then what we are getting? Then we can see here del Q1A2 and del Q1A2 will get cancelled out in the left hand side, and del W1A2 and del W1A2 will get cancelled in the right hand side. So what will be remaining here? We will have del Q2B1 minus del Q2C1 is equal to del W2B1 minus del W2C1. And dear students, we can see the equation 1, that del W2B1 minus del W2C1 here written. And we all know from here, from this figure, that del W2B1 and del W2C1 will not be equal with each other. Why? Because work transfer depends on path, not the end points. We have already discussed, right? So this del W2B1 will not be equal to del W2C1, right? So the difference of del W2B1 minus del W2C1 is not equal to 0. In equation number 2 we can see it, right? So from equation 1 and 2 here, equation 1 and 2 here, we can see del Q2B1 minus del Q2C1 is also not equal to 0. If the right hand side of equation 1 will not equal to 0, then obviously the left hand side will also be not equal to 0. So from this equation, del Q2B1 minus del Q2C1 is not equal to 0, we can write that del Q2B1 is also not equal to del Q2C1. Means in this figure we can see del Q2B1 is also not equal to del 2C1. So we can write, or we can say a statement for this: though the paths of though for path B and C end points are same, that 1 and 2, right? Here also we have written, though for path B and C end points are same, but heat transfer is different for different paths, and hence heat transfer is a path function. So that's why, dear students, we can say our heat transfer is also a path function like work transfer. So it is not a property and it is an exact differential. If somebody asks you to prove that thing, so you can prove it very easily by by deriving these equations. So first consequence of first law of thermodynamics is heat transfer is a path function. Important points with respect to heat transfer and work transfer, right? So both are not properties. We all know heat transfer and work transfer are not properties. These are path functions. Both are inexact differential, right? Means the difference of 2 points is different of paths is different. No, values of different paths is different. So both are inexact differential. Difference is not exact, right? Both are path functions because they both crosses the boundary. That's why they are path functions, and both are boundary phenomena. So these are the important points related to heat transfer and work transfer. Now, dear students, we can see second consequence of first law of thermodynamics. First consequence was heat is a path function. Now second consequence is a energy is a property. Energy is a property. How energy is a property? So we can also understand this particular thing by writing equations. So we have already discussed this graph 1a2, 2b1 and 2c1, right? So process A is the going process, and process B and process C is the returning process on point 1. So end point 1 and 2 are there. So here is a process A and here is a process B and C. So as we have discussed earlier, we were having these equations: del Q 2b1 minus del Q 2c1 is equal to del W 2b1 minus del W 2c1. What we are observing here, that we have to take this 2b1 term one side. So del Q 2b1, and from here del W 2b1 we have taken it in left hand side. So del Q 2b1 minus del W 2b1 equal to del Q 2c1 minus del W 2c1, right? So 2b1 we can means del Q minus del W for 2b1 process. For 2b1 process is equal to del Q minus del W for 2c1 process. So we can see here del Q minus del W for one process and del Q minus del W for other process are equal, right? Means difference of del Q minus del W is equal for different paths. So here it is written, though the path B and C are different, but the quantity del Q minus del W is same for both the paths, and hence del Q minus del W is independent of path. That means when the final values are same and the difference is same, that means del Q minus del W is independent of the path because it is getting the same value as a property. So therefore it is a property, and this property is known as energy. We have given the name of this property as energy. So del Q minus del W 2b1 equal to del Q minus del W 2c1 is equal to dE. Why we have written here D? Because D is exact differential. Energy is a property. That's why we have written dE. And why we were writing del because it is a path function and it is an inexact differential. So dear students, second consequence of first law of thermodynamics is energy is a property. Right, from this equation we can see, if we'll move further, then how we can write this equation. Del Q minus del W 2b1 equal to del Q minus del W 2c1 equal to dE, and we can write del Q minus del W 2b1 equal to dE, and when we will remove that 2b1, then we can write it like del Q is equal to dE plus del W. So del Q equal to dE plus del W. This is first law of thermodynamics for a closed system undergoing a reversible or irreversible process. What we have get in first law of thermodynamics, that summation Q is equal to summation W. and that was the equation of first law of thermodynamics for a cyclic process. But here we are getting the expression del Q equal to dE plus del W. This is the expression for first law of thermodynamics for a closed system, but this is for a process. Del Q is equal to dE plus del W. So this is very important note. The equation del Q equal to dE plus PdV is valid for a closed system undergoing reversible process only. Why? Because PdV is only valid for reversible, and this del W is not only valid for reversible. This is valid for reversible and irreversible both, but this PdV is only valid for reversible process. We had derived this only for reversible process, because del W equal to PdV is valid only for reversible process. So dear students, we can see here this E is our total energy, and total energy consists of kinetic energy, potential energy, and U is our internal energy. Internal energy is basically the energy associated with the molecules. So change in total energy is equal to change in kinetic energy, potential energy, and internal energy, and we can write here change in total energy as change in individual kinetic energy, potential energy, and internal energy. If kinetic and potential energies are negligible, then our total energy will be equated as internal energy, because we are discussing here with mainly with the molecules. So the molecules energy is basically internal energy is the energy associated with molecules. So we consider here that our total energy is internal energy. So we can write here del Q equal to D plus del W, and we can write del Q equal to du plus del W. So internal energy is associated with the molecules. So our first law of thermodynamics for a process will further become del Q equal to du plus del W. So till now we have seen two consequences of first law of thermodynamics. First was heat is a path function, and second we have seen energy is a property, right? Internal energy is an extensive property. Extensive property is a property which is dependent on mass, right? And intensive property is a property which is independent of mass. Okay, like the example of extensive property which is dependent of mass is volume, right? And intensive property is pressure and temperature. So the unit of internal energy is joule or kilojoule, and specific internal energy of an intensive property. Why we have said specific internal energy? Because when internal energy is getting divided by mass, then it will become specific. So when it is earlier it was dependent on mass, but when it will be divided by mass, then it will become independent of mass, so it will become intensive property. The equation del Q equal to du plus del W is the first law of thermodynamics, right? Equation for a closed system undergoing a process when kinetic and potential energy changes are neglected. Okay, dear students, now we will move to our third thermodynamics, right? So third consequence is energy of an isolated system is always constant.
Your phone's in airplane mode, so I can't help you with that at the moment.
So third consequence, energy of an isolated system is always constant, right? So energy interaction means energy interaction is zero, because in isolated system we are not going to cross the boundary, and if we are not going to cross the boundary, then heat transfer and work transfer both will become zero, as we know that heat and work are the boundary phenomena, right? So we can see here del Q equal to D plus del W. So del Q equal to 0 and del W equal to 0. So D will become 0. So E2 minus E1 equal to 0, and E2 equal to E1 equal to constant. So third consequence of first law of thermodynamics is energy of an isolated system is always constant, right? Now the last and the fourth consequence, students, that perpetual motion machine of first kind PMM1 is impossible. What is perpetual motion machine? Perpetual, the meaning of perpetual is continuous also. So continuous motion machine. So continuous motion machine of first kind is impossible. So what is this? Let us understand. The first lie states that the general principle of conservation of energy is neither created nor destroyed, but can get transformed from one form to another. So what is PM? This basically statement is the statement of first law of thermodynamics, that energy can neither be created nor be destroyed, but can be transformed from one form to another. So in this PMM1, what we have to understand, that there can be no machine which would continuously supply mechanical work without some other form of energy disappearing simultaneously. Such a fictitious machine is called perpetual motion machine of first kind, or PMM1. So the PMM1 is thus impossible. Here it is clearly saying that there will be no machine which would continuously supply mechanical work. In this figure we can see that without getting heat, this dotted arrow is showing there is no heat, right? So without getting heat, this engine is producing work, so it is impossible. This is not at all possible. This is a fictitious machine, and so that's why this is impossible. So this is our PMM1. Converse of PM1 is just reverse. The converse of above statement is also true. There can be no machine which would continuously consume work without some other form of energy appearing simultaneously. Obviously, in this figure, the converse of PM1, in this figure we can see we are supplying work to a machine, but it is not producing anything, right? It is not producing any kind of energy. So this is the converse of PMM1, right? So this is basically our fourth consequence of first law of thermodynamics, that perpetual motion machine of first kind PMM1 is impossible, right? So that's all for the today class, dear students. I hope you all have enjoyed the class. Thank you.